Today, we're going to go over some of the most commonly misunderstood misconceptions for AP Physics. And we'll go over top five. So let's just get started right away with number one. Number one, distance versus displacement. Distance is how much ground you cover, and it's always positive, always scalar, meaning that it has some kind of a quantity. But on the other hand, displacement is a vector because it has a direction, meaning that it can be positive or negative, and it also has the scalar quantity like distance does. So distance is just how much you move, but displacement is your final position minus the initial position. So let's go over some examples. Let's say we have a home and we have your school. Let's say we start from home and we walk 3 kilometers east to get to school. And then we come back from school back to home. And that's another 3 kilometers. So in this case, your distance is 6 kilometers. But your displacement is actually 0 because it's the same place that you started off with. So if your final is same as your initial starting position, your displacement is just 0. It does not matter how much you moved. So let's do some quick practice. Let's say we have a circular track, and to go around the circular track once, it's 400 meters. So that means the circumference is 400 meters. Let's say we start here, and then we just go halfway. Let's try to find the distance and the displacement. So for distance, since going around the entire circle is 400, it's just half, 200. But displacement, it's a little bit more tricky because what you have to do is you have to do final position minus the initial position. So you actually have to get this distance, which is 2 times the radius or the diameter. And I'll just do the math for you, so it's 127 meters. Now let's move on to misconception number 2. Force equals ma. This is wrong. Most students just go, oh, we have gravity and gravity equals ma. Well, it's wrong because our Newton's second law actually says that sum of the forces equals ma. So you can't just say this force equals ma, this friction equals ma, gravity equals ma, normal force equals ma. Those are wrong. You have to add up all the forces that's acting on an object, and then the sum of the force, which is sometimes called the net force, this is equal to ma. So let's talk about some real life examples. Let's say you push a heavy box across the floor. Let's say you're applying a force 50 newtons and friction pushes you 30 newtons backwards. So that means you have to think about all the forces acting on it. So technically we have gravity going down. This is usually Fg. And we have a normal force because it's on the floor. So the floor is supporting this heavy object. And then you're pushing the object here. So this is called the applied force. And there's also friction pushing back at you. So we have to look at these 4 forces and add them all up. And thankfully, normal force and gravity, they cancel each other out. So that makes sense because it's not moving up or down. It's just moving left or right. So we have to add up the friction force and the applied force. And then we'll get a net force of 200 newtons. So we have sum of the force equals 20 newtons, and this is equal to ma. So just make sure you're adding up all the forces, and that is equal to ma. Right. Let's keep going. Misconception number 3. Centripetal force and centrifugal force. So now we're talking about a circular motion. This is centripetal force. And we also have some fictitious force. This is not real, and most people get confused because they think this is real. Centrifugal is not real. Centripetal force is. Centripetal force is actually the net force as well. This is the centripetal force, which is also the net force, and this is equal to mv squared over r. And it's always, always, always directed towards the center of the circle. So if you're going around the circle, it's always towards the center. But centrifugal force, it doesn't exist, but it feels real because sometimes, think about a car going around the circle, you feel like you're being pushed out of the circle. Or think about a merry-go-round, it feels like your body is trying to go outside the circle. But that's not real. That's a common misconception. So when a car is turning around, your car is actually pushing you towards the center, and that's why it feels like you're going outside, but force is actually acting on you towards the center of the circle. Okay. Misconception number 4. Conservation of energy. So we say that energy is conserved, but this is too simple. This is not always the case, especially if you're just thinking about the system. So if you're thinking about the system, energy might not be conserved. So in physics, we learn kinetic energy, and we learn potential energy, and gravitational potential energy, and spring potential energy. And here, sometimes, even when we add up all these energies, they might not add up, meaning it might not be conserved. And it's because of some special cases, such as an inelastic collision. So let's say the two cars crash and they crumple up together and they stick. And because they don't bounce, think of elastic meaning bounce. So it's an inelastic collision because they do not bounce. They stick together. So in this case, momentum is conserved, but not energy. Energy is actually lost to heat and friction, and it goes out of the system. So think about heat. It goes away. It goes towards air, the environment. So if you look at just the cars, the two cars, the energy is not conserved. Okay. All right, let's look at the final misconception. Translating from linear to the angular space. Now, this is very difficult because you have to be able to convert linear space into angular. And they're not exactly equal all the time. So let's think about momentum. Momentum is equal to mv. So you might just think, oh, v is equal to r omega, which is angular velocity. So you might just think, oh, then angular momentum is mr omega. But that's wrong. It's different. Because now we're in the angular space, you have to think about the mass, the speed, and also the radius. Because depending on how far away you are from the center of the circle, your momentum can change. And this is because of angular momentum. So if we're using this equation to start off with, we actually have m r omega times r. So then we get mr squared times omega. And remember, mr squared is actually rotational inertia. So that's why we get L, angular momentum, is equal to inertia times omega. So think about a skater, like an ice skater. If you have your arm out, your radius is bigger. So that means because your momentum is conserved and your radius is bigger, that means your angular velocity is slower. Versus when you have your arms really close to your body, because momentum is conserved, your angular velocity increases. So that's why if you look at the figure skaters, they spin faster once they start putting their arms together. So let's do a quick practice. Let's say we have a disk, and let's say the inertia is 2 kilometers times meter squared, and it spins at 6 radians per second. Now, the inertia actually changes. Let's say it contracts to just 1 kilometers times meter squared. So now we have to figure out the new omega. Well, this is pretty easy because just like momentum in linear space, angular momentum is also conserved. They need to be equal. So, since angular momentum is I omega, this is 12. So, we also need to make the second angular momentum equal to 12. So, omega has to be 12 radians per second. Here's the thing about physics. It's most students struggle and it's hard not because the math is impossible, but because you have to think logically and also correctly. Most students they do think logically. Whatever they're trying to solve the problems and they reason through, it makes sense. Like they're thinking logically. But most students they start from the wrong idea. So if you're starting to think that your concept is off, even if you have perfect logic, you'll get the wrong answer. So just make sure you get the concepts down and you're using the right ideas, not the correct ideas.